Well, thank you very much. My name is Fred Roosta. I'm the last one in the line of series of Michael Mahoney's postdocs. Julian was the first guy, Kimon gave a talk the second day, Alex was this morning, and I'm the last one. That says something about our relative importance, I guess. But we kept the best for last, so hopefully. Let me acknowledge my great collaborators. I've been lucky to work with these guys. Peng, a PhD student at Stanford. Jiang is in the audience. He just finished his PhD, moving on to Facebook. He's going to present a poster on part of the results that I'm going to talk about. So please feel free to stop by and talk with him. Chris and Michael, also professors at Stanford and here. So before I get into any details, let me get something off my chest and make a disclaimer. The results that I'm going to be giving today, both on technical and also on philosophical aspects, they work when you're talking even more than massive data, essentially humongous data, ginormous data. Maybe I should have even reserved the talk for some future conference, FGDS, future ginormous data sets or something like that. Whatever I give you, whatever result I give you, take that with that grain of salt. That it works when you have a lot of data, which might not have today, but hopefully in 10 years maybe we'll be able to have. The problem that we're trying to solve is very simple. It's just as you're minimizing a function over some domain or some set, and the function is a sum of some other functions. And I'm sure all of you have seen examples of this before. Any field that you work in, if you're essentially working with multiple measurements, multiple observations, chances are you can write down your problem same as this. However, the emphasis here is that the number of functions in the summation is very large. And the domain that you're trying to find your parameter in is high dimensional. So it's either or both. They are not mutually exclusive. So that's the set of the problem that I'm trying to solve. If you're in machine learning, I'm sure you are familiar with this format. You probably call every one of those functions to be like, loss function or corresponding to the ICE observation that you have. GLMs, SVMs, graphical models, neural nets, all kinds of problems. You can write them that way. If you're like me, coming from a scientific computing background, you probably have used a different lingo. We use like misfit instead of loss and measurements instead of observations. One example that is near and dear to my heart is like PD inverse problems, which I did my PhD work on, where all these little functions are corresponding to, in fact, some kind of a PD solve where you're trying to infer the parameters involved in that overall PDE model. So you end up having billions or millions and tens of millions of these little measurements, and you can see that the problem would become immediately intractable, especially when you're talking about a PDE on a grid which is really fine. So parameter space is high dimensional as well. So regardless of whatever domain you're coming from, I think we can all agree upon one thing, that when it comes to large-scale data, classical optimization models essentially are just not capable of doing the job anymore. They go belly up. And the reason mostly is because a lot of these iterative schemes, they have a very high per iteration cost. And that's the reason why we can't use them, because they essentially don't, it's not that they don't work, it's just they take a long, long time to make progress. And that's why a lot of smart people have looked at designing some variants of the classical methods, classical optimization iterative methods, where they're not only essentially have a low per iteration cost, because at the same time, not only low per iteration cost, but also they're also fast at achieving the goal. Because one algorithm I could give you which has a very, very low per iteration cost, and that's just doing nothing. But it's not going to get you far. So essentially the goal is to come up with a method that not only has a cheap per iteration, but also has to be very fast at achieving the goal. Now, one big class of these classical models where, classical models where classical optimization techniques where all of us are familiar with. They're essentially called the first order optimization methods, where the reason why we call them first order because they only use first order, aka gradient information, to make progress. The classical one is, the most famous one is gradient descent, going back to Cauchy. So everybody knows this, and also they have some really nice theoretical properties where if your function is, the overall function you have is, if it's convex and smooth, then you have a sublinear convergence rate depending on 1 over the k being the iteration counter. And if you have a strongly convex and smooth function, then you can actually show that gradient descent has a linear convergence rate. So for what it's worth, it's fast. But the problem is that in the setting we're looking at, that is computing this gradient involves computing the gradient of each one of those individual functions and sum them together. And because we're talking about ginormous data, that means computing that gradient is very costly. So what people have done, they have looked at variants such as SGD, which we're all again familiar with. The bottom line is that SGD or mini batch versions, what you do, you somehow uniformly, non-uniformly, that's up to you. You pick a subset of these, the indices that you're given, and you pick the corresponding functions, you compute the gradients, and you compute the empirical average, and take that as your approximation to a true gradient, take a step along that direction, and repeat that process. Very nice because it has a very cheap per iteration cost. For example, SGD, you only need 1 gradient evaluation. However, it suffers from the fact that the speed of convergence slows down dramatically, comes down dramatically. For the smooth function, remember gradient descent had 1 over k. Now we lose square root of k. Now we go to 1 over square root of k, significantly slower. This is for SGD. For a strongly convex, we were linear if we were using gradient, but now we are sublinear 1 over k. So what people did, they said, we are going to make modifications to SGD so that not only we can keep the per iteration cost of SGD, which is nice, but also we can increase upon its speed and try to achieve the speed of the full gradient descent. And as you can see, this is just a few examples of existing methods out there that sets out to achieve this goal. There are so many methods out there. It's just every year you look at NIPS and ICML, there is a few new methods coming out, a little bit of variants of each other or some major differences. But regardless, there is a lot of interest and a lot of effort in designing a lot of first order methods that kind of mimic gradient descent and SGD, cheap and fast. Now, I come from a scientific computing background, so the situation was a little bit perplexing to me because, you know, scientific computing community had long given up on first order methods. We stopped using them a long time ago because we realized they're just not going to solve our problems. They're always hindered by the condition number of problems. The problem we were looking at, a lot of them have really moderate, even moderate condition problems. The first order methods just simply wouldn't cut it. We wouldn't be able to answer the questions we're after. We wouldn't be able to find the optimum. And yet I saw many smart people in machine learning spend significant amount of time designing new first order methods. Now I was perplexed by this. And the image that I have in mind, the next picture is going to be a little bit politically incorrect, but that's literally what I could think of state of affairs these days in machine learning, where it is somehow some kind of a marriage, but a marriage without a prenup that you can't get out of. It's just like you're stuck and you just have to work with first order method regardless. Now, I wondered, I mean, why is this so? I mean, why people don't make use of other techniques that are out there that are faster, that scientific computing people use. And in fact, I give you a little story. I was in a conference some month ago, and there are like wonderful theories and techniques coming out in first order methods. And I went and talked with all these guys, and I said, did you try Newton method? And they said, no. I said, why didn't you try Newton method? They said, well, we didn't. I said, why? It's slow. I said, did you try to see if it's slow? Did you try if it worked? No. Well, so that means there is some kind of a maybe work to be done to change the mindset that exists in machine learning. So I started asking around, why do people use first-order method? Why everybody loves first-order method in machine learning? Essentially, everybody answered that, hey, cheaper per iteration. I totally agree with that. I have no problem with that. We, in fact, knew it a long time ago. Everybody agrees upon that. Yeah, first-order methods are definitely cheap per iteration. But the second thing, I had no idea what it was. They said that it avoids overfitting. Now, I had no idea what overfitting is. What does it mean? I mean, you write down min if you want to fit it, right? What does that overfitting mean? And they said, hey, you don't want you don't want to, because they said, well, it's true that we write down min if, but that technically that's not what we mean. We mean that we want to mean something else that we don't know what it is. So instead of doing that, we try to minimize what we are given. But because that is probably, it's not what we want to minimize, we don't want to minimize it, because then essentially, the result that you're going to get is not going to be the one that you were after. And I said, okay, that's kind of interesting, but how are you going to do that? And they said, well, I mean, gradient descent has this property that in a moderately to ill-conditioned problem, it's just going to get stuck at some point. It's going to bounce around, zigzag around, not going to make any progress. I said, hey, that used to be a bug in my community. They said, no, this is a feature in this community. We actually use it. It's a form of regularization. And I realized, okay, that's interesting. So I started learning about these things. What it means to overfit and what optimization actually can do. So in mathematical terms, the objective of a lot of machine learning is this, that you assume that your data that you see today comes from some kind of an unknown distribution, that you don't know what it is. And you're also given some kind of a loss that you measure how good you're doing. And what we're trying to do at the end of the day, if someone, so you make those assumptions, and then you say, hey, someone has given me a bag full of hypotheses. And by hypotheses, I mean, say you're fitting a linear model, different lines with different slopes and intercepts are hypotheses, say. So you're given a bag of different hypotheses. You want to pick one that on average has a really low loss on average across all possible realizations of the data. The ones that I've seen today and the ones that I haven't seen today and tomorrow I'm going to see. They call it generalization error or prediction error. Well, obviously we can't do that because we don't know what this distribution is. So we are given just n samples of this from this distribution. So what we form what is called the empirical risk minimization problem, where this is exactly the same format as the finite sum problem that I introduced the first slide. So if you see finite sum in any machine learning literature, chances are what's going on underneath the point is empirical risk minimization, trying to approximate that. Okay, so let's say we've used some algorithm on the empirical risk minimization and we find an optimum there. And someone also gave that the best possible hypothesis that does the best on average across all data points. Here's a very interesting, very deep, interesting results. There are so many others with the same flavor. I just gave you one that I could parse. And that is, they say, well, if I find the hypothesis coming from that empirical risk, and I use that to explain unseen data, or all the data, possible data, on average, I'm probably going to be worse than the best possible hypothesis, but I probably will not be too bad. I will do worse, but not by so much. And this so much is characterized by this quantity, which is inversely proportional to the number of data points that you see, and directly proportional with this VC dimension of your hypothesis class, which is a measure of complexity of your model. So your model is the linear, it's a very simple model. Say, if you're fitting a polynomial with high degree, then you have a more complex model. So if you have some model which is relatively simple or a finite dimension in terms of complexity, in the regime that I made a disclaimer at the beginning, that's ginormous data when n is really big, then this error is actually small. So there is no risk of overfitting anymore. If you're actually spending all the time to come up with alternative to SGD because you can't afford to compute the gradient. Gradient is probably the easiest part of optimization to compute. If your n is so large that you can't compute the gradient, so that means probably you want to get to the bottom. Otherwise, this is it's a contradictory objectives in my mind. And one might ask, okay, so n is large, we want to get to the bottom of it. So I changed my question, and if not to me at least, the answers would be, if I'm living in the regime that you have a lot of data, cheaper per, any algorithm we want to find has to have a cheaper per iteration property. I cannot argue with that. But this overfitting now, it's up for debate to me. I don't buy that argument anymore, because if you have a lot of data and you desperately want to find a method that's going to be able to make progress, then maybe, you need to switch to something else, because we actually do want the minimizer. And now okay, gradient descent can never get you to a minimizer in bad problems. So what can you do? You can go to some, god of science, Newton has already given us that, but we forgot about it. Heresy, we forgot about it. Now we're essentially going to make it come back. So the Newton method, we all know what it is. It's a canonical example of second order methods which use gradient and Hessian information. It has really nice theoretical properties. If your function is convex, it has super linear convergence rate. Remember, gradient was 1 over k. Here is not only linear, but also super linear. Then you have if you have a strong convexity, you have a quadratic. Back there was linear. Now you have a quadratic. Nice. But the problem is per iteration cost is extremely high. And that's one of the reasons why this method probably is not flying a lot in many communities. So what people started to do back from the 70s, they started to approximate the second order information cheaply, which gave rise to a whole host of methods, deterministic kind of approximation methods called the quasi-Newton methods, BFGS, LBFGS, and variants of that we all know. But recently people tried to leverage the randomized approximation, measure concentrations, and all these new theories to approximate the Hessian randomly. And this work kind of started maybe 5-6 years ago from a group with Nocedal and Mertens in Toronto. Recently, our own Pilanchi and Wainwright did the work for the first time, introduced sketching into the business. Montanari in Stanford has done some work on subsampling. And we have done also a series of work on subsampling the Hessian and the gradient. So, but I would like to invite people who are interested in this kind of work to kind of form a coalition, because we need to kind of form a coalition, and in the spirit of political season, make our motto to be, let's make Newton great again. and move forward. I already have an approval of one guy, so. How are we going to analyze our problems? I'm just going to give a little bit of math here, and how much time do I have? Because the chair left. Okay. So the general framework where all these optimization algorithms come is that at every iteration you form some kind of an approximation to a function. Locally, say we are here, and this is the function you want to minimize. You form some kind of an approximation. You take the minimum of that. It's obviously not the minimum you want, but you hope that it's closer, and you do it like that. Depending on how you approximate your function locally, you get a different method. For example, if your G is full gradient and your H is full Hessian, you end up getting Newton method. If your G is full gradient, H is identity, you get the gradient method, and so on and so forth. There are all kinds of methods. You can put a whole host of methods onto this framework. What we looked at was the subsampled Newton methods, which is you can subsample two things. You can subsample the Hessian, and you can also subsample the gradient. So we looked at subsampling just with the Hessian, which has been done so far. People didn't look at including the gradient subsampling. And we also looked at the case where not only you can subsample the Hessian, but also you can subsample the gradient. Essentially, subsampling means pick random coordinates, or form those gradients, those Hessian, take the average, and take that as my approximation. You can take these samplings of the gradient Hessian, independently or dependently, simultaneously. We have results for all kinds of different things. So this is a summary. It's an overview, or what we have done in our group, where we looked at global convergent algorithms, that they approach the optimum at any point, and also we looked at their local properties. And we recently done some interesting work on how we can incorporate non-uniform sampling. It's not a trivial task as opposed to so simply uniform sampling. So I'm just going to give you quickly a few results. Part of our results, which I'm going to just use full gradient and only do Hessian sampling. There's no time to go into all different kinds of variants. I have some standard assumptions in convex optimization problem related to the smoothness of the problem and strong convexity and so on and so forth. I'm not going to bore you with it. Let me make a quote from a big hero of mine, Professor Nocero. Michael knows I keep talking about him. I've never had an honor of meeting him, but I'm really fond of his work. And so I quote, he says, "We want to design methods for machine learning that are not as ideal as Newton methods, but have these properties. First of all, they tend to turn towards the right directions, and they have the right length, i.e. the step size of 1 is going to be working most of the time. And we have to have an algorithm that scales up for machine." He's essentially given us a blueprint or a guideline of what we need to do to come up with new methods in order to be able to solve modern problems. Now, there are a few things here that essentially embody what he's trying to say. First, he's saying that not as ideal as Newton method. Okay, so he's not as ideal. That's probably too difficult to do, but at least they should be good enough. The second thing is that turn towards the right directions. He immediately is talking about curvature. We need to look at curvature somehow. And really interestingly, he talks about the right length. And in particular, step size of 1 needs to be working. Because you know, step size of 1 is a natural step size for the Newton method. And at the end, obviously, he talks about that being scaling up. So let me just quickly say if we actually manage to achieve at least partially what he's suggesting. So he talks about scaling up. What it means is that we need to have a sample size that's either independent of the total number of measurements we have or at least a lot smaller. And also, if you're talking about bigger dimensions, we need to allow for inexactness in our algorithm, that you compute the direction inexactly. The second requirement is that turn towards the right direction, curvature, aka preserve the spectrum of your true Hessian as much as you can. So subsampled Hessian needs to preserve that spectrum as much as you can. Not ideal, but close, meaning that, well, Newton is really fast locally, so at least you need to be able to mimic that to be fast. Maybe not as fast, but you have to be fast enough. And the right step length, meaning that unit step length needs to work for your algorithm at the end of the day. So requirement 1 and 2 can partially be satisfied by this simple lemma, which says if your sample size is large enough, which this large enough depends on the condition number of problem. Again, this might be a very large number. That's why I made a disclaimer early on. What you can do, you can preserve the structure of your Hessian. Subsampled version can be to epsilon close to your true Hessian. So not only you can preserve the spectrum, but also hopefully this sample size is going to be much smaller than the n that you're working with. The third idea, not ideal but close. Well, if we subsample like that, we're going to end up with some kind of error recursion. And this error recursion is really interesting because it has a linear term and is a quadratic term. So x super k is the x at the current next iteration, x at the current iteration. It's interesting because the coefficient that's multiplying the linear term just depends on how accurately I'm approximating the Hessian. However, the other one depends on some quantities related to the problem. So what is this telling us? It's telling us that when I'm close enough to the optimum, where this linear term essentially dominates that quadratic term, I'm going to be able to get a rate that is independent of my problem. So there is no notion of condition number in the convergence rate. And you want to have a convergence rate of order 1/4. I'll just compute the right epsilon here, plug it in there, made subsample like that, I'm guaranteed to achieve that. There is no getting stuck in any corner. There is no any bouncing around here. You're just going to keep going down. So there is a simple algorithm we can do, and there is this result that if you're close enough, then you get this linear rate. If you want faster, you can also make it superlinear if you're allowing yourself to approximate this Hessian more accurately as you go along. You can also have some other superlinear where the approximation grows, but really incredibly slow at the rate of a log of an iteration. And finally, a unit step length that he said needs to work. So our algorithm so far was local. We also made some global algorithm that you can, for example, incorporate Armijo line search and make it a global. Obviously, at the beginning, you're not going to have the step length of 1. But this result says that, hey, if you include the Armijo line search and you're willing to sample large enough, then after a certain number of iterations, this unfortunately it's large. But again, it's a qualitative guide of what Newton can do. If you wait long enough that finally you're going to hit a regime where all step size of 1 are going to be accepted in your line search, and you're going to keep moving forward with step size of 1, which is interesting because another quote from him, and he says, any optimization algorithm for which the unit step length worth has some wisdom in it. And it's too much of a fluke if the unit step length accidentally works. So that's a reassurance that what we're doing, hopefully at least, is kind of moving towards the right direction. Michael, how many? Okay, so there are some silly examples on logistic regression I've done. They're not by any means huge, but they're huge enough for a smart guy like me that I had to sit at my laptop and watch this. I don't have enough patience, so it's just small enough. We need to do a lot more, and we are in the process of actually making all these algorithms, run them on real problems, large-scale problems. I just want to give you one example. When, for example, the condition number is 10 to the 6, it's not really huge. You can easily get it in practice. Maybe not, I don't know about what happens in machine learning, but I know in scientific computing this is considered extremely well conditioned. If you have a condition number like that, if you look at the purple line, which is the gradient descent and superimposed by an accelerated version of it, essentially what's happening, they're not making any progress whatsoever. They're just flattening out. And what you see in a lot of machine learning literature and presentations, you're seeing this little corner here. You see that? The gradient descent is going faster than other stuff. It's because they're only looking at really, really low digits of accuracy. And that's the problem I was referring to. They say, okay, we don't want to overfit. But hey, maybe you do want to overfit. And if you want to overfit, then you're in trouble if you want to use first order methods. Because say even LBFGS, which, you know, in my opinion, it's not really a second order method, it's 1.5 order method because you always use gradient to approximate Hessian. They also have difficulty driving the error down. But look at all these Newton methods. Exactly, X is for exact, NX is for inexact. I didn't get to details what I mean, but all these second order methods, including Newton itself, they have no problem driving the error down. I could have even gone further than that. And the case when it's really in condition, then you know there's no hope for any other method. You have to do second order method. Now, just a few words on non-uniform sampling. So this is all was kind of theory about uniform sampling, but the problem is in practice, if you have discrepancy among your data points, you have some outlier functions. You need to sample order n in order to be able to capture that bad guy there. So we thought about non-uniform sampling. Is it possible to do non-uniform sampling? Essentially have a sampling strategy that is not only independent on n, but also it's just immune to this all kinds of business that, I'm getting the data, I don't have to worry about if there's an outlier. If there's an outlier, I'm going to catch that with low sample size. And we did some work with recently that, yes, if your problem admits certain form, you are able to leverage some recent results and introduce some sampling schemes such as the norm based on norm squares and based on some new notion of leverage scores, where if you do that, then you can introduce some really significant improvement over the complexity of the non-uniform Newton method over the uniform counterpart and over even the sketching counterpart that people have done. I won't have time to go into details. Jian Yang will have a poster tonight, and he will particularly talk about this aspect of the work. That's why I didn't put much on it, because he's going to talk about it. Please feel free to stop by, talk to me, Michael or Jian, if you're interested. And yes, thank you very much. I hope it didn't go over time.